Section 3.5 exercises. First question asks us to find the domain of the function g of x divided by x squared minus 25. Well, for a domain of a rational function, the denominator cannot be 0. So we will find the values of x that make the denominator 0. Taking the denominator x squared minus 25 and setting that equal to 0, and then bringing the 25 over to the right side, we can then take the square root of both sides. So x is equal to plus and minus 5. So x cannot be 5 and x cannot be negative 5. And one way we write this using interval notation is to write the domain being the interval negative infinity to negative 5, union negative 5 to positive 5, union positive 5 to plus infinity. And that's a fancy way to say x cannot be 5 or negative 5. Problem 2. Find the domain of the rational function h of x. Taking the same approach as above, we take the denominator and set it equal to 0, and immediately realize that x squared would have to be equal to negative 25. And that is not possible, which means there are no values of x that make the denominator 0, so the function is defined for all x. So then the domain would be all real numbers, or we could write the interval negative infinity to plus infinity. Problem 2. True or false? The notation x arrow a with a little plus sign in the top right corner means, well, it does not mean that x is increasing without bound. It means x is approaching, that's the interpretation of the arrow, and it's approaching the value of a, and it's doing so from the right. So if we were to draw the picture to represent this, there is our x-axis there. Here is our value of a, and x is coming in this way on the right side of a, getting closer and closer to a. Problem 3. Find the vertical asymptotes of the function g of x. First here, we have to remove any common factors. Which we can do since the denominator factors x plus 1 times x minus 1. And we can divide out our factor of x minus 1, leaving us a simplified version of 1 over x plus 1. Then to find the vertical asymptotes, we find where is the denominator equal to 0, and that'll be for the value x equals negative 1. So that means the vertical line x equals negative 1 is a vertical asymptote, and we will abbreviate that by VA. This is a vertical asymptote of the graph of g of x. Problem 4. Find the horizontal asymptotes for the function f of x. Okay, here what we're going to do is we're going to divide all terms, numerator and denominator, by the highest degree term that appears in the denominator. This is an algebraic technique to find horizontal asymptotes for any rational function. Here, our highest degree term in the denominator is 3x squared. So we will take every term in the numerator, take 9x squared and divide it by 3x squared. In the denominator, we divide each of those by that highest degree term. Simplify next, and that'll give us 3 in the numerator, and in the bottom, 1 plus 1 over 3x squared. Now, we ask, as x gets very, very, very large, what happens to the value of the y coordinates? The function will then approach. 3 remains to be a 3. And in the denominator, we have 1 plus 1 divided by a very large number shrinks to 0. And the functional value of the y coordinates will approach 3. So that means the line y equals 3 is a horizontal asymptote for the function f of x. Problem 5. Graph the rational function 3x minus 3 divided by x minus 2. Okay, we'll use a multi-step approach here where we'll find a lot of information and then translate that to the graph and see if we can draw the graph of the function. First, we'll look at the y-intercept. So the y-intercept, of course, means when x is equal to 0. So we'll do f of 0. And computing that, we'll have 3/2. So the y-intercept is 0, 1.5. That's where the graph will cross the y-axis. Next, we'll find the x-intercept. And that will occur when the function is equal to 0. So taking the function 3x minus 3 divided by x minus 2 and setting it equal to 0, we have to solve that for x. The only way that fraction can be 0 is if the numerator is 0, and that will give 3x is equal to 3, or x is equal to 1. So we have 1, 0 as our only x-intercept. Also note that this has multiplicity of 1, so the graph will actually cross that x-intercept at 1, 0. So we got the y-intercept, we have the x-intercept. Let's add to that any vertical asymptotes or horizontal asymptotes. Vertical asymptote will be where the denominator is 0, provided the function is already simplified and no common terms can be removed. And no common terms can be removed, so we'll take the denominator, set it equal to 0. That gives us x equals 2. So the vertical line x equals 2 would be a vertical asymptote. Find a horizontal asymptote. We'll look at the highest power that appears in the denominator, that is x to the first power, and we'll divide all terms by that highest degree term. So 3x divided by x minus 3 over x divided by x, and 2 divided by x. We'll simplify that, giving us 3 minus 3 over x divided by 1 minus 2 over x. And now ask, as x gets very, very large, what happens to the function? The function will approach 3 minus 0 divided by 1 minus 0, or 3. So the horizontal line y equals 3 is our horizontal asymptote. Let's translate that information down below on the graph. First, locate our asymptotes. Vertical asymptote is at x equals 2. So we'll go down here, and we'll note x equals 2, and we'll draw that in here. And that is our vertical asymptote. We have a horizontal asymptote at y equals 3, so we'll indicate that and draw that in there. Now we'll plot our points. We know we have an x-intercept at 1, 0, so that's right there. And we know the function must cross there. What else do we have? A y-intercept of 1.5, so 1.5 is right about there. Okay, now often with rational functions, they are trapped by their asymptotes, and I would anticipate the curve being in this area here. So I will draw that in through the x and y intercept and down along the asymptote. Curves love to head straight for these asymptotes. On the right side of this vertical asymptote, the curve is either here or it's up in this quadrant here. And since it cannot be here, there would be an additional x-intercept. The curve must be located up in here. What I suggest that we do is we plot a few points to help verify that. F of 3 will give us 6, so we can plot that point. 3, 6 will be right about there, so that'll help out. And one more point, F of 5 equals 4, and we can plot that point, 5, 4, right about there. So our curve right in there. And if you need to plot an extra point over here when x is -5 or -6 to help verify that the curve stays below the horizontal asymptote, you can do that.